So again, we've got a skier that starts from rest at the top of a frictionless incline that happens to be 20 meters vertically from the lowest point in this question. The skier is going to ski down a frictionless slope, so he's not going to lose any energy to heat or anything in this section. But by the time the skier reaches the bottom, once the slope levels off, the snow gets a little bit worse and heat starts to get generated. And eventually all of that energy is vanished and the skier comes to rest. And we want to know how far they have to travel along this flat portion before they come to rest. Now the nice thing about energy, we could start with my initial energy, which we know is potential, and then work out the energy at the bottom of the slope where there's no losses, where we know that's kinetic. And then start the question again once we know the kinetic energy or the speed at the bottom. You're starting with kinetic energy and it's all being converted until we finally have nothing but heat energy left. Everything has been removed and it's all been converted to heat energy as it comes to rest. But we don't have to do it in stages. That's the nice thing about energy. This is my initial point and this is my final location. So we don't have to do the middleman. So all of the energy before can equal all of the energy after, and let's just write our overall energy conservation equation. So I can start with kinetic and potential and any additional work done. So any additional forces that might push on the skier, and that gets converted to a final potential, a final kinetic, and any heat that's generated. Now, in this particular question, my initial velocity was 0, so there was no initial kinetic energy. Nobody's pushing on the skier with any extra forces, so no work is being generated. At the final location, the skier is at the lowest point in the problem, so no potential energy. And it does say he finally comes to rest, so there's no kinetic energy. So all we started with was potential, and all that potential energy eventually gets converted into heat. Well, what creates the heat energy is friction. So we say that the work done by friction is equal to our thermal energy produced. So work done by friction is simply force of friction times distance, because they're both parallel to each other. So as an equation, it looks like this. mgh initial is equal to force of friction times distance. Now my force of friction is mu times the normal, and just like in our regular dynamics, my force of gravity acting on the skier is straight down. My normal force cancels it off, it's straight up, otherwise that skier in that flat part would be moving vertically. So I can say my force of friction is equal to mu, instead of the normal, I can say mu mg. And once again, when I put all this together, my masses cancel, and I can go ahead and solve for d. So d is going to be equal to g times my initial height, all divided by my coefficient of friction, times g again. Notice the g's cancel, and I end up with 20 meters, my initial height, divided by my coefficient of friction, which they say is 0.210. And when I do that, I end up with 95 meters before that skier comes to rest. Now, can you solve this problem using dynamics? Well, absolutely. Now, with dynamics, we'd need to know a little bit more. If I look at the skier when he's actually slowing down, I start with a free body diagram, like I always do in dynamics. So I've got my force of gravity down. Now this is while he's in motion, and my normal force up. And while he's in motion, friction is pulling him back. So normal and gravity cancel each other. My net force, therefore, is the force of friction. So F net's always ma. My force of friction is mu times the normal, which we've just discussed as mg. I use this to solve for my acceleration. So my acceleration is mu times g. Then I can switch to switch to kinematics. V initial, V final, acceleration, time, and we're trying to find distance. Now my acceleration, it's slowing down, so we say it's negative mu g. My initial velocity, we have to figure out by the time it reaches the bottom of that slope. So we'll come back to this in a second. V final is 0. I don't know time, I'm trying to find d. So if I avoid equations with t in it, I'm going to use this one. V final squared is V initial squared plus 2ad. Now how do I find my initial velocity? Well, if you recall right at the beginning, we said we could do this in pieces. My initial potential energy, by the time it reaches the bottom of the slope, all gets converted to kinetic. So I could say, and I'll just do it in blue as a little side calculation, my initial potential energy gets converted to kinetic. Cancel it all off, solve for V. Like that. This final velocity in this equation becomes the initial velocity in our equation above, and we crank it all out and we'll get exactly the same answer.